So here we are in part 2, and we saw in part 1 a few of the basics of ER diagrams, the idea of modeling entities and relationships in particular, and we began to see some of the reasons why it's important to break things into entities instead of modeling them as relationships. But one thing that we missed out on was the ability to constrain relationships to require that they always exist or that they only exist a certain number of times. And so the main part of part 2 will be discussing what are called cardinality constraints, which is the ability to enforce that a particular relationship always exists for a particular entity and some destination, or that it only exists a certain number of times. We're also going to talk a bit about the aliasing problem, which occurs if we have two discrete entities that for some reason might overlap. So we'll begin with this application here, which clarifies one aspect of relationships, which is the ability of a relationship to wrap back to the same entity more than once. So the only examples we saw in part 1 of relationships were relationships with only two legs. So the relationship went from one entity to one other one. Although I mentioned at the time that a relationship in general can tie together any number of entities, and we'll see in this example that it's often natural for it to tie the same entity back to itself. So we're going to construct an extremely limited model to approximate the basic idea behind Twitter, which is we have a bunch of accounts. Each user creates tweets. They could choose to create no tweets in the entire lifetime of their account. Each tweet has some text and a date, and each tweet has exactly one author. So this is a key point. We were not going to allow a tweet to have no authors. It must have an author. It can't have 2, it can't have 0, it must have 1. And then a tweet can have 0 or more hashtags, doesn't have to contain any. But a particular hashtag can be used in any number of tweets. And so we notice from this idea that a particular hashtag, referring to a hashtag as an object, can be used in any number of tweets. That's sort of implying that we might want hashtag to be an entity. And then users can follow other users. They don't have to, but they can follow as many as they want. So we can create entities for the basic pieces here. As I mentioned, we sort of caught on to that idea that a hashtag the same hashtag can appear in multiple tweets. That sort of implies hashtags have to be a thing unto themselves. So there's a hashtag, and we're going to model some relationship between it and a tweet. We have a user there identified for the time being just by their account name, and then a tweet has content, so some text of some kind, and the date it was created. So we get that the user creates a tweet, I guess. So just like last time, remember that we like to design the relationship names to be readable across the relationship. So user creates a tweet, or a tweet is created by a user. It's a bit awkward, but we try and read it across the relationship. A tweet contains a hashtag is contained in a tweet. So that's one thing. We can model those basic relationships pretty easily. The problem is, what do we do about this? So a user follows a user. And you might be looking at this and thinking, well, it's pretty obvious what follows has to connect to, but let's reason through it a little bit. So we could do this. We could say, okay, so a relationship has to connect an entity to another entity. A student takes a course, an instructor teaches a course. Okay, I guess a follower follows somebody else, a followee, I guess. But both of those are just users. So the follower has an account, the followee has an account. And now the tweet could have been created by the follower or the followee. You can already see that's a bit of a mess. But now consider that somebody who follows somebody else could themselves be a followee. Somebody can both follow somebody else and be followed themselves. So it muddies the waters quite a bit about exactly what is the true relationship between these two entities. Are we missing something? Maybe it's obvious that we are. So that's not really a good idea. It really clutters our diagram. It makes the model of the data way more confusing in the service of one constraint that we might have a better way of modeling. So, I mean, it's confusing. It also makes duplication. The slides sort of prioritize, this creates duplication. We know already duplication's a dirty word. I would argue that, we can resolve some of the duplication later, but this makes the diagram almost unreadable already. So we could do this. We could create a relationship called follows and just have both legs of the relationship sit on the same entity. Now, in this case, there is a sense of order to the relationship. So one user follows another. That's not a symmetric relationship. And so in this context, we generally like to label the different legs of the relationship because it's not obvious. So we call one of the users is the followee and one of them is the follower, and they participate in the follows relationship. We're allowed to label the roles in any relationship. So we could say, well, the user is the creator of the tweet, and then this is the created tweet. But you might see that labeling these two legs doesn't make much sense because it is obvious from context. The user creates the tweet. So clearly there's a user in a tweet. The tweet must be the thing being created because we only identify the user as something that's capable of creating things. So it's not logical in that case to label the legs of the relationship because we want to keep the diagram relatively simple. We want to make it so that it's intuitive, so that humans can read it. But in this case, up here, the follows relationship is asymmetric. So it's important that we identify the two distinct roles a user can occupy because in different instances of that relationship, they could end up occupying both. A user can be both a followee in one context and a follower in another. And so this is pointing that out. It's worth considering we don't have to do that every time a relationship wraps back to the same user. So the friend relationship, this is using social media as an example, but this works in real life. I hope it works in real life. The friend relationship doesn't have roles because two users are friends or they aren't. So it's a symmetric relationship, and therefore it's not significant for us to identify the follower or followee. So we don't need to label the legs of the relationship in this case. And if we don't have to do it, we shouldn't do it. We should keep the diagram looking clean. So this now reflects all of the constraints we were working with, and that does resolve a question many people have, which is, can a relationship wrap back to the same entity? So the answer is yes, but it doesn't resolve the problem of tweets with no author. So we saw last time that this relationship indicates that there may be a connection between a particular user and a particular tweet. It doesn't require that there ever exists such a connection, so there could be 100 users and 100 tweets and no instances of the create relationship. It also doesn't preclude having one user associated as the creator of all the tweets or one tweet being created by all the users. We, however, want in the model, we've designed this system to include some constraints on who can participate in the relationship and how often they can do it. In particular, we would like to enforce the constraint that every tweet is associated with exactly one author. So not 0, not 2, not 5, exactly one. We can't have a tweet with no author. So we need a way of enforcing that, and the diagram as written doesn't provide us that way. It is a many-to-many relationship. The creates relationship is a set of pairs of user and tweet. So it's many-to-many. And in some cases, there could be no author associated with a tweet. So just to be clear, we don't want a one-to-one relationship, but we also don't want a many-to-many. We don't want to enforce that every user has exactly one tweet and every tweet has exactly one user, just half of that. We want every tweet to be associated with exactly one user, but still put no restriction on how many tweets a user can have. They can have 0, they can have 1,000. So what we want is to generate a one-to-many relationship. Now we'll see that we do have the option of generating one-to-one relationships later. The one-to-many relationship is modeled by an arrow. This is a strict one-to-many relationship. A tweet has exactly one author. And so we use this rounded arrow. This particular bit of notation, the rounded arrow, the semicircle, is very unique to our ER diagram format. And I've noticed that if you go looking at other formats, they might use boxes and diamonds and ovals, but the notation that they use for arrows, semicircle versus solid arrow versus hollow arrow, tends to be quite distinct. So they might make different choices, which is one more reason not to use other formats. Don't take that risk, even if it looks similar. So you might notice in this case, the arrow only appears on one end. So that begs the question, how should we read this? Well, you'll notice the arrow does point in a direction. So the key here is only read the arrow's effect when you are walking along the relationship in that direction. So we should read it as a tweet is created by exactly one user. So we just walk across the relation, and if we see the arrow pointing in the same direction that we're walking, we read the effect of the arrow. In this case, the semicircle means exactly one. So a tweet is created by exactly one user, but if we read the relation the other way, we don't see that arrow at all. It's not pointing in the same direction. A user creates a tweet. So there's no restriction from user to tweet. A user can create as many tweets as the user wants, 0, 1, 1,000, whatever, but a tweet is created by exactly one user. So that's my recommendation for how to read the arrows. We're allowed to put arrows on as many of the legs of the relationship as we want, but on the ones that it doesn't affect, it has no implication whatsoever. So a user, by this arrow, is not restricted to only create one tweet. It's only restricting the number of users that can create a particular tweet. And this slide is again pointing out, you better use our format or you're taking some risks here. So the rounded arrow is an example of a strict one constraint. We'll see in a minute that we sometimes don't want to actually require that. We might want a tweet to be allowed to have 0 authors, but not 2. So we want to allow at most 1 of something. But this constraint is saying exactly 1. So we have this fragment here. And this goes back to part 1 where I mentioned that we have to be very careful about what assumptions we encode into our data model. Here, it's reasonable. The way that we've defined what a tweet is implies that it can only have 1 author. If we've encoded that into our database, if we put this arrow here, we have to live with it forever. But in this case, maybe it's reasonable. I mean, what is a tweet anyway? Twitter invented that idea. They can define what it means. Here, though, we're modeling the enrollment again, and we need to be a little bit careful whether we think this is actually a legitimate constraint. We're allowed to impose this constraint. So the way we would read this diagram is we would say a student enrolls in exactly 1 major. So every student must have exactly 1 major. A major may be enrolled in by students. So there's no restriction going in that direction. So we have a many-to-one relationship. We need to ask ourselves some questions about whether that was a good idea. So first, why is this not necessarily realistic in general? So I know it's a good idea. A student should have a major. Fair enough. So we add that constraint. But adding the constraint is enforcing it in all circumstances. It's not trying to convey our ideas of the best situation. It is saying what is possible in the universe, not what is a good idea. So the issue here is that maybe there's a time when a student has no major. When a student first enters, they might be undeclared. This, as modeled here, this constraint wouldn't allow that. Every student must have a major. It also might be the case that students are allowed to take double majors. This constraint wouldn't allow that either. A student enrolls in exactly 1 major. So even though our typical conception of what a major is seems to imply a student has 1 of them, it is not a universal constraint. There might be times when a student permanently has 2 majors. There might be moments when a student might temporarily have 0, or maybe even temporarily have 3 or something. We need to consider all of those before we make the decision to add a constraint like this. And it's worth thinking about if you end up working with a system. So if somebody hands you a database where this constraint's already been encoded and they say, we need the ability for students to have 0 majors or 2 majors. You need to work around this. You can't change the constraint. It's already there. The database has been designed around that constraint. It may not be possible to remove. Is there a way of working around it? That's dangerous, and maybe by talking through that we can understand better why it's important to get the design right on the first pass before we implement it into a database. So before we get to that, let's consider that first, we may have students with no major whatsoever. That can happen. They may be in the process of declaring something. In this database, that isn't allowed, and that's no good. This is maybe an improvement in the sense that we're saying here a student can enroll in a major. It's somebody else's problem to figure out how many they're supposed to enroll in. This completely removes constraints from the relationship. So a student can enroll in a major can be enrolled in by students. Great, okay. So this would allow a student to have 0 majors or 1 or 1,000. We might argue that that's a little bit too unconstrained. Maybe we want to impose some reasonable constraint, but we want to avoid having to work around it. So as I said a minute ago, if we have a constraint like this, we might end up needing a student to have 0 or 2 majors or 3 majors, and we have to work around the constraint. The way you might work around this is you might define a fake major, a phony one, called undeclared. And if the student isn't in a real major, you enroll them in the major undeclared. But maybe you can appreciate that isn't really a good solution. That is a hacked together solution. It's duct tape. If you're designing a database, you don't want to rely on having to add duct tape later. And the same is true if you want students to have 2 majors, but you have a constraint like this. If you want a student to be allowed to major in both music and computer science, you could make up a phony major called music computer science altogether, or music/philosophy or something. But if it really is a double major, 2 distinct majors, you don't want to have to do that. And it turns out that adding extra records like that creates all sorts of other problems for really representing the relationships between data. Because if you have a student, if you have 2 nominal majors, music and music/philosophy, where this is meant to be a phony representation of a double major, if I go asking you, how many students major in music? Well, actually, both of these students are majoring in music. But if I just go searching for music majors, I don't find this one because it's actually a different name. And so that's dangerous, and that's one of the reasons to be very careful about encoding constraints. So we want maybe to encode some amount of constraint into this. We don't necessarily want this situation where they could enroll in 1,000 majors. Suppose we decide a student can have at most 2. So they can't have 3, even though even that might be a bit excessive. We might want to allow them to have 3 or 4, but limit it at some reasonable number like 5. On the logic that if we have a constraint limiting to 5, then if we attempt to enter invalid data, it would get caught and wouldn't make it into the database. Having a constraint that allows any reasonable circumstance, even slightly improbable ones, but catches obvious errors, can be helpful. We don't want students to be in 1,000 majors, even if we don't expect that to happen. It would be nice to encode that into our database. So we have this option. The rounded arrow says, if I put a rounded arrow here, I'm saying a student is enrolled in exactly 1 major. But if that's too strong for us, we could use this solid arrow. So a solid arrow is saying 1 or 0. So in this context, it would be a student enrolls in 1 or 0 majors. So that would allow the possibility of them having no major at any given moment. Now, it still wouldn't allow 2 majors. So we have another option as well, which is we can just write an arbitrary constraint here. We can write, so a student is enrolled in less than or equal to 2 majors. Okay, so they can be in 0, they can be in 1, they can be in 2. And actually, arguably, if you have the rounded arrow, you're basically writing in the constraint equals 1. And if you have the solid arrow, you're writing in the constraint less than or equal to 1. Although generally it's better to use the arrow if you have an arrow available. If you want to represent a weird constraint, like less than or equal to 2 or 5, or greater than 3 and less than 7, then you have to write it in. Although it's generally frowned upon to write those in unless you have good justification for why you're using such a strange number. Usually if you see those constraints written in, certainly in my experience, it appears to be a case of somebody being overzealous. Really, you don't need a constraint at all, but you're writing one in because you feel like a constraint ought to be there, even if it isn't really implied by the context. So we have this option. So we should now be familiar with the full array of different constraints we can add. The vast majority of constraints you see tend to be arrows, rounded arrow or solid arrow. We really would rather avoid using this unless we have to. And this slide is also observing, yeah, we don't actually need any arrows if we can write them in, but maybe we can appreciate that the arrows are often easier to read once you get used to them than the written in constraints are. So it is actually possible to have one-to-one. So I talked earlier about many-to-many and many-to-one, but it's possible to have one-to-one relationships. It turns out that usually if you think you need one, so every car contains exactly 1 engine. Okay, well, that's fair enough. Maybe I want a constraint like that. But do I really want a constraint? Every type of engine, every engine is contained in exactly 1 car. I suppose the same type of engine could be in 2 different models of car. Often when you think you need a one-to-one constraint, you don't. You may not be thinking carefully enough about the possibilities. It's also possible that if you have a one-to-one constraint that is legitimate, what you really should be doing is combining together the entities that it bridges. You don't necessarily need to have the 2 different entities if they're tied so closely together. Every driver has exactly 1 brain. Every brain is inside of exactly 1 driver. Well, why even have this? Just have 1 big entity. The driver can have a name and the driver can have thoughts. There's no need to do that. We'll see a few examples of cases where one-to-one relationships are sort of necessary. There's one key issue that'll show up in part 3 and part 4 where we do appear to have a one-to-one relationship that might be helpful. But generally speaking, if you think you need one, you likely don't. So, and the reason is because they're way too restrictive. The one-to-one basically is locking pairs of entities together. So there's no real freedom between the two types of entities. And usually the reason that they get added is because we haven't thought carefully about one direction of the constraint. In many cases, the one-to-one relationships that I see are actually many-to-one relationships where we've been a bit overzealous. So maybe this is a bit better. Every car contains at most one engine. I suppose it's possible for a car to not contain an engine at the moment. A driver drives, well, okay, at any given time, somebody can't be driving two cars. So a driver drives 0 or 1 cars. Well, that's fair enough. A car can't have 2 drivers, but a car could have 0 drivers. So every car is driven by at most 1 driver. That also makes sense. This is a flippant example over here, so I mean, those could have been merged. So now I want to talk about this. This is another issue. This isn't really a cardinality constraint problem, but it's lumped into part 2 because if you look at it at first, it seems like a cardinality constraint might help. The reason you think that is because right now all we've learned about is entities, relationships, attributes, and cardinality constraints. And if all you have is a hammer, everything looks like a nail. So we're going to see we need something a little bit better than the hammer for this. So I want to model this very basic system of doctors and patients. So patients visit a doctor. For the time being, just for keep things simple, let's assume patients have a name and we don't care too much else about them. Doctors have a name, a phone number, an email address, and a practice address. This is a deliberately long list of attributes to try and nudge us away from a certain type of brute force solution to this problem. Doctors contain so much information that we do not want to duplicate the doctor entity on the diagram. Now, some doctors are surgeons. Well, that's neat. Fair enough. You might think about that and say, well, I guess I could add an attribute to the doctor, like a Boolean value. Yes or no, is this person a surgeon? Also, some doctors are specialists. If they are a specialist, then they have some sort of specialty. They don't have a specialty if they're not a specialist. It also points out, and this is very significant, surgeons could be specialists. A specialist does not have to be a surgeon, and a surgeon doesn't have to be a specialist, but there are some doctors that are both. But here's the issue that creates, I think, the most trouble for us. Surgeons perform surgeries on patients, and we keep track of the date of each operation. Now, you can already in your head maybe think, okay, so surgeons perform surgery on patients. The surgery itself has a date. And you think, well, if that were the only constraint I had to worry about, it sounds a lot like surgery is a relationship between surgeon and patient. But doctors are surgeons, but not all doctors are surgeons. So what do we do about that? We need some way of representing that a doctor could be a surgeon or not, but we also need some way of making sure that arbitrary doctors that aren't surgeons don't get involved in this. And so we need something a little bit more powerful than what we already have. Now, the first approach might be something involving cardinality constraints. And so we could look at this. We could say, well, before we worry about that surgery relationship, let's think about just the basics here. So there's the doctor, and I think that looks pretty good. The doctor has a phone number, name, practice address, and an email address. And just to be very clear about this, a doctor does not have to be a surgeon or a specialist. So we need to make sure that there is an ordinary doctor entity on the diagram. And so there is. Okay, and then a patient visits the doctor. Great. So what do we do about surgeon and specialist? Well, we could try this. Let's make surgeon its own entity. It'll certainly make it easier to create relationships that only connect patient and surgeon. The way we do that is we say, well, a surgeon is its own entity, but every surgeon is going to be a doctor. They're exactly one doctor. If you're a surgeon, you can't be 2 doctors, you have to be 1. So we define this strange-looking sort of one-to-one relationship, and then we relax it in the other direction. A doctor can be at most 1 surgeon. They can't be 2 surgeons, but they could be 0. A doctor might not be a surgeon. And then same for specialist. So a specialist is exactly 1 doctor. They are required to be a doctor, and a doctor can be a specialist. It turns out that this actually also sort of interpolates the idea that a surgeon can be a specialist, because the same doctor can have the relationship defined between them and surgeon and them and specialist. There are some consistency problems here. To be honest, the biggest problem I have is, so what defines a surgeon? What are the attributes? We know that an entity, an instance of this entity, is defined by its attributes. What are its attributes? Well, it doesn't have any. So how do we define it? What does it mean to be a surgeon? Really, being a surgeon is just a yes or no. It's a Boolean condition on being a doctor. But the problem is, if I want to represent the surgeon entity, how do I refer to it? Do I give surgeon a name separately from the name that the doctor has? So if I do this, then what if I end up with a situation where I'm tying a particular surgeon to a particular doctor and the names don't match? That looks a lot like that dangerous redundancy that we're trying to avoid. So the issue really here is that surgeon isn't really its own entity. Surgeon is somehow subordinate to doctor. And if you think about it, it looks a lot like the subclass relationship. Even, I'm not sure why you'd be thinking about that. It looks a lot like the subclass relationship you'd see in a class hierarchy. So we've got this parent class, doctor, and there are these child classes, surgeon and specialist, where a surgeon, I mean, really, a surgeon does have a name and a phone number and a practice address and an email. They're just inherited from this root entity, doctor. The issue is that this cardinality constraint doesn't capture that because it's a relationship. It's a constrained relationship, but a relationship is meant to connect two distinct, independent things to indicate their connection. Even if it's constrained, it is understood that the two things have their own identity in some way and are being tied together. But the surgeon is pretty much contingent on the doctor and the doctor's information. Now, we'll see the concept of something called a weak entity shortly, where a weak entity could be used to model this in some cases. It would certainly be a better, I guess, less heavy-handed than this modeling. But in the meantime, we actually have a much better way of modeling this type of relationship. One thing I want to be very careful about here is that although the conceptual idea of a surgeon is a doctor and a specialist is a doctor is quite similar to the idea of classes in a class hierarchy, like in Java. So in Java or C++ or whatever, you might have some interface called list, and then you've got a linked list which inherits all of its behavior, and you've got an array list. And the key thing there is that, of course, they inherit everything from the parent class list, but a linked list isn't an array list. There's nothing shared between linked list and array list besides what they get from above. If you wanted to define some overlap between them, you would make one a descendant of the other. That does not hold here. So this idea, just like I said in part one, we want to be a little bit careful about drawing the analogy between ER diagrams and types in a language, because there are some differences where if we get too comfortable with that analogy, our conceptual understanding can fall apart a bit. So we don't want to use independent entities. We really want to avoid that for lots of reasons. But even if we could do that, we're making a real mess by not having attributes on an entity. And we need to have some way of indicating a surgeon is a doctor. It has all the same properties as doctor, plus one extra one, the property of being a surgeon. And so we have an option. It's a special signifier on the diagram. It's the is specifier. You might see some sources, the book I think might do this a couple of times, call it is a. Inside the triangle it writes is a. It just doesn't work for me. So the triangle is forms a way of describing an entity as being a subtype of some other entity. And the way we draw it is we make the triangle point at the parent. So a surgeon is a doctor. A specialist is a doctor. And the is relationship, because it's so specialized, it's just defined to mean exactly what we expect by this. A surgeon is a doctor. Not every doctor is a surgeon. There could be no surgeons, but if you have a surgeon, they are a doctor. If you have a specialist, they are a doctor, but there may not actually be any specialists. The advantage of the is specifier is that it also brings with it all of the semantic information of the subtype. So we assume surgeon doesn't need any attributes of its own because it inherits all of the attributes of doctor. So a surgeon has a phone number, a name, a practice address, and an email address, and so does specialist. The slides agree, I guess. And so because we now have this, and surgeon is now a valid entity, we are allowed to entangle it in a relationship. In this case, it's a three-legged relationship between patient, surgeon, and the surgery entity. Now, the reason why surgery as an entity is there instead of just being a function of the relationship is that this does allow a particular surgeon to perform multiple distinct surgeries of different types on the same patient. because, I mean, arguably, even inside of like one long operation, several distinct surgeries might be performed. So if we were to make surgery a bubble, so an attribute, we'd have that problem we saw in part 1, where the relationship between patient and surgeon either exists or doesn't. We can't have multiple copies of it. By entangling surgery as its own entity, now a patient has a particular surgery performed by a particular surgeon, or they don't. So they can have different surgeries performed by the same surgeon because each one would be a separate instance of the relationship. It's worth considering even that doesn't go far enough, because maybe there's a case where the same surgeon needs to perform the same surgery on the same patient more than once, and we can't do that with this model. That's one of the reasons why it can be quite tough to settle on a set of entities to use. One thing to observe about the is specifier is that unlike in a class hierarchy, it is not mutually exclusive. A surgeon is a doctor, a specialist is a doctor, but there is no requirement that a surgeon is not a specialist. You could have one doctor who is both a surgeon and a specialist, and that was allowed by the original model. Interestingly, it turns out that we're not actually allowed to define the is-not relationship. The ER diagram doesn't give us any easy way of deciding that a surgeon may not be a specialist. The is specifier allows somebody to fall into both subtypes. If we wanted to restrict somebody from being in more than one subtype at a time, we would have to fall back on adding some software constraints to our eventual database. The ER diagram doesn't really give us an easy tool for that. So what we've seen here is a few things off to the side. So that discussion I just had about this three-legged relationship, patient, surgeon, surgery, that maybe indicate we've got quite a bit more to develop as far as when do we define a relationship, when do we add more entities. What we know is we now have enough notation to model pretty complicated systems. If we're at the point when our discussion should be when do I need an entity, when do I need a relationship, maybe that's a good place to be because it means we know enough notation. We've expanded our vocabulary outward enough to begin solving complex problems. We still have a couple of other things we have to resolve, so part 3 is going to wrap those up. One of those issues is what happens if we have something that is a separate entity, so it's not a case of a surgeon is a doctor. What if we have two entities that are tangled together where one entity can't exist without the other? We know that surgeon can't exist without doctor because surgeon needs to inherit all the properties of doctor. But that's remedied because surgeons are doctors. What if we have a similar situation where it's not that one entity is another entity, it's that one entity relies on another entity. So part 3 will resolve that. That'll be what's called a weak entity. We can also talk about weak relationships. And then we can finally begin resolving what do we do when we have to describe some particular relationship and we need to confront this problem of being able to exist more than once. And so when do we create new entities? So it'll be in part 3.